So for this very last lecture, I just kind of want to reiterate what the goals of this course and the next course are. And that is that I'm trying to basically give you a general understanding of most of the advanced statistical techniques that are used in the research and the practice of the fields of psychology that SIUE focuses on. This is not necessarily meant to make you mathematical experts in statistics. This is also not even necessarily to make you masters in the application or practice of these statistical techniques. It's hard to determine what your future will bring to you, what types of research articles you will mainly read, and what kind of analysis or methodology you use, if any, in your practical fieldwork. What the goal of this course is to give you enough exposure to be able to figure out potentially what statistical techniques should be used, and if necessary, enough pre-knowledge that with a little bit of research and a little bit of review of the slides from this class and the walkthroughs, that you'd be able to be competent in that analysis. So this first semester, we've actually covered a fair amount, including general theory, general methodology, and descriptive statistics. We've also talked about between subjects ANOVAs, within subjects ANOVAs, factorial ANOVAs, mixed model ANOVAs, and now ANCOVAs. And that, of course, built upon the knowledge that we started with, looking at simply t-test correlations. Now, moving into next semester, we do have some additional things to handle, including coming back to multiple regression. There's a lot more we can do with it than we've covered in this semester. Looking at multivariate analysis. So everything that we covered in this semester was considered a univariate test, and that is specifically uni meaning one, but variate meaning the actual outcome. We've always looked at the effect of individual or even multiple predictors, interactions, and even nonlinear terms, but always on their effect on a single outcome. We're going to look at techniques that allow us to look at multiple outcomes or DVs in one single analysis. We also are going to look a little bit more at non-parametric tests. So every test that we've looked at up until now have been parametric tests. And parametric, again, is focused on that DV. The DV has always had the assumption that it is a continuous or ratio data. It's basically interval or ratio, a continuous variable. And even multivariate analysis typically assumes this, but we're also going to be looking at particular tests that can look at non-parametric, in other words, categorical outcomes. So we've got a lot more to look at, and we've got a lot more to cover. But again, our goal is not sheer mastery. Our goal is exposure and practical use. And as a part of that practical use is, again, just trying to figure out what works for you individually. So I've used various tools and various charts through this semester, and I'll continue into next semester. But really use what works for you. So this is what makes the most sense for me. I simply ask, whenever I'm looking at any study, how many variables? So that's the first question. And if there's only one, that pretty much tells me I only have the t-test or z-test for independent measures. If there's two variables, and this includes my DV, then it simply is a question of what are my IVs? Are they categorical or continuous? And if they're categorical, do I have two levels or more than two levels? And again, that'll tell me from that point on what statistic to use, with one additional question: is it between or within subjects? If there's more than two variables, then again, it's continuous or categorical. If they're continuous, or any combination of continuous variables, I'm probably at multiple regression. If they're all categorical, I'm at some form of factorial ANOVA. So again, this is just a way to kind of hopefully help you later down the road be able to determine what statistical technique you should be using just based on the variables you have. How many, and are they categorical or continuous? Another way is to look at it through design methodology, not necessarily statistics, and just again a reminder there's different ways to categorize research designs. We can look at them as experimental, quasi-experimental, or non-experimental. So experimental, we have taken full control of our predictors. Our independent variables are under our control, and we can start to make a solid argument for causation. And again, that gets to Mills' canons, that idea that we have to have a statistical relationship, we have to be in control of the independent variable, and we have to rule out all other causes. Quasi-experimental means something of those canons are missing somewhere. Generally speaking, what it means is we don't have complete control over our independent variables, or we have not been able to rule out all other possible confounds or explanations. And finally, non-experimental designs, where we do not have any form of random assignment, group categorization, or control of either the covariates, other causes, confounds, or the actual IVs themselves. They're just pre-existing. We're basically doing descriptive work. Designs can also be categorized by the number of independent variables we have: one-way designs with a single IV or factorial designs with multiple IVs. And finally, we can look at how people are exposed to the various levels of those categorical IVs, which gives us either between participant designs, within participant designs, or mixed designs. And all designs have strengths and weaknesses, and all designs can be, in certain situations, the design you should use. Experimental designs are great at causation, but they're not very good at actually generalizing to the real world because they're usually fairly artificial. Non-experimental designs cannot handle causation, but are truly representations usually of what's actually happening in the real world, as they're very close to reality or are actually just measuring what's happening naturally in an environment. Another way we can look at it is simply the DV is a categorical continuous, and the IV is, again, categorical continuous. If both our DVs and IVs are all categorical, we either have chi-square or discriminant function analysis. Those are non-parametric tests, and we'll be looking at those next semester. If the IVs are all categorical and our DV or DVs are continuous, that's the t-test, ANOVA, ANCOVA, factorial ANCOVA, and MANOVA, MANCOVA, and factorial MANOVA. And all MANOVA is a multiple analysis of variance. It's a multivariate technique where we have multiple continuous outcomes. If everything's continuous, our IVs and our DVs, we're looking at correlation, regression, multiple regression, and potentially, if all we're looking at is actually measuring the actual measures themselves, factor analysis. And again, we'll be dealing with factor analysis, additional multiple regression techniques, and MANOVA next semester. And finally, if our DV, our outcome, is categorical, but our IVs are continuous, that's logistic regression. Again, a non-parametric statistic that we're going to cover next semester. So again, I'm presenting these not to overwhelm you, not to make you fear next semester, but just as little quick guides that you can come back to later when you're having to ask yourself, okay, it's 10 years since I had stats with Dr. Nadler, but I've been asked to look at a series of continuous variables on a continuous outcome. This slide will help you kind of decide what statistical technique should I be looking closer at. And again, remember that no matter what the statistical technique is, we still have the steps. We always have to check the assumptions. And that can be both a theoretical or methodological check, but that can also be a statistical test. We have to look for outliers in our continuous outcomes. We may have to conduct mathematical transformations, or if we find that we violated assumptions, such as Levene's test, we may have to use adjusted statistics. Once we've done our assumptions, if we have a complex enough design, the first thing we're going to report is the omnibus test results. So the F, the R, the T, the Z, the B. What was the omnibus test of all of our potential interactions or of main effects within our model? What were the degrees of freedom? What was the P? And if significant, what was the effect size? Then, depending on the complexity of the design, we may have to look at within factor differences, post hoc tests, so categorical variables with more than 2 layers or 2 levels. Then we need to examine interaction differences with simple main effects. And finally, at the end, we have to put it all back into English, reporting the actual significant differences in terms of relationships, positive and negative correlations, or means and standard deviations. So just again, an idea to remind yourself that we've covered a lot. You are now well versed in most univariate statistics, and honestly, in my personal opinion, compared to most other master's programs that are out there, you now have what you would be leaving with in most master's programs. A lot of master's programs have basically a basic intro to methodology class and then one statistics class. We've rolled those 2 into this class alone. What we're moving into next semester is actually going to give you a set of skills and exposure to advanced statistical techniques that a lot of other master students may not have. So definitely recognize that you are getting a detailed education in statistics for the level of education that you're getting. Just also don't obsess with trying to become a master of all these techniques. That's not our goal. You can actually get a PhD just in statistical techniques, quantitative methodology, or psychometrics. You're taking 2 classes. But those classes are designed to make you relatively decent consumers of statistical techniques and hopefully methodological research articles, and also enough knowledge to be able to do the practice of a particular technique with just a little bit of review if you need to. So another thing I just want to talk to you about is also that most of the statistical techniques that are used today are honestly somewhat outdated. They were designed over 100 years ago based on basically probabilistic concepts. And this cartoon is actually something that I actually kind of like because it reminds us that there's different techniques out there. And as we move forward further and further into the computer age, eventually we will be moving away from most of the techniques we've talked about. Now, I've often been saying this, in fact, I've been saying this for a decade, and yet almost every research article I read is still looking at ANOVAs, MANOVAs, multiple regressions, and they are useful techniques. And one of the reasons they're sticking around is that when we compare them to more advanced computer models, a lot of times for all of that advancement, the computer models aren't that much better at finding relationships. In other words, they are useful tools, and they're tools that can still work. However, this is a quick cartoon that explains the difference between a frequent statistician, which is basically what I'm teaching, and a Bayesian statistician that looks at the overall probability. So did the sun just explode? This neutron detector measures whether the sun has gone nova. Then it rolls 2 dice. If they come up both as 6, it lies to us. Otherwise, it tells us the truth. By the way, the chances of getting boxcars on 2 dice are about 1 in 20, or about 5%. Let's try. Detector, has the sun gone nova? Rolls the dice. Yes. That means you're 95% sure that the sun has gone nova, because 95% of the time when it says yes, it's telling you the truth. But 5% of the time when it says yes, it's not. So the frequent statistician, the probability of this result happening by chance is approximately 0.02. Since that is below 0.05, I've concluded that in fact the sun has exploded. The Bayesian statistician would look at the probability of this occurring based on the base rate of whether the event itself is likely at all. And of course he responds, I bet you $50 it hasn't. This does point out a problem with us tying ourselves to p-values. A lot of the times our p-values are based on the idea that whatever we're actually predicting has a base rate or a chance of occurring that is the same as across any other study. When the reality is that if I find a p of 0.07, but what I found is a very surprising and very strong result, there's probably a good chance that's actually reality. While if I actually find a statistical significant effect of 0.03 and a very small effect that is very unlikely, the chances are actually that I very well might be wrong, and I've just increased the chance of me finding that p-value by the large sample size. Now, Bayesian statistics, basically calculating the Bayesian chance of something, requires you to actually calculate base rates. It's very complex, and generally we only see it in computer models. But again, I just wanted to bring this up as the last thing we talk about in this class so that you do recognize that what we're looking at is kind of traditional statistics. We're looking at traditional frequent or frequentist statisticians based on the p-value concept. And there are other ways to look at these, and sometimes more appropriate ways.